Welcome to Wednesday. Hope the assignment's going well. I will go back to my office right after class today. I guess you get the benefit of coming to class and hearing this. I'll go back to my office today and then stay there for about 45 minutes to an hour for anybody who has questions on homework. I also have office hours tomorrow morning from 10 until noon. So feel free to stop by Gates 201 if you want to go to my office hours. And then, of course, there's regular office hours with the TAs this evening and tomorrow as well. The assignment is due tomorrow. Hopefully it's going all right. Remember, this is a real file system you guys are actually looking at. So all the little nuanced parts to it, well, that's real life. That happens in real programs. So you're getting a little bit of a taste of that. Let's see, I put a joke up here. The barman asks what the first one wants. Two race conditions walk into a bar. So I know it's hilarious, isn't it? So the joke is, you always have to explain your jokes if they're not that hilarious, right? So the joke is that this is a race condition. We haven't really talked too much about race conditions yet, but we will start to see many race conditions. We've seen a few here and there. A race condition is simply when two things are happening simultaneously and you don't know and you can't predict which one will actually get to where it's trying to go first. That becomes an issue if you're doing things like trying to wait for something to happen, or rather not wait for something, if you forget to wait for something to happen and it may be out of order from what you kind of expected. So you have to think about that. It makes programming concurrently tricky because you have to think about that. So today we're going to do a few examples where we're going to see race conditions and we're going to see one way of handling them. Okay. So this is what I introduced on Monday. We're talking about signals now. Okay, and signals are a way to send a message, basically, or not even a message, basically a way to say to another process something has happened. You don't even get to say like any message itself. The best you can do is you can actually pass a signal number, which is the actual signal that gets sent, but you don't get any other information. If you want to pass other information to the other signal, you have to do it in such a way that both processes have access to it, which generally would mean shared memory or a file or something like that, and that becomes a little bit trickier to do too. So it's not like you have this situation where you're just signaling another process and then being able to tell it lots of stuff. It's got to be a logic sort of thing, like when this signal happens, you're going to do this because the signal happened. That's what we're going to do. We're going to see examples as we go through this. Okay, a signal handler is it's a function that you write that goes into a process, and when that signal arrives at the process, the signal handler gets called. Okay, and the ones that we're going to focus on are when a child has some change of state, when it ends, when it stops, when it's continued. And we haven't even talked about how you continue a child that's stopped, but we'll get there. And that's a function that you write, and it gets called when that happens. Okay? All right. There are lots of different types of signals. As we said, there's signals that happen because something bad goes wrong, like you tried to divide by 0, that sends a signal. Or if you do Control-C, well, your program gets a signal that it actually can't block. It actually is going to kill your program, generally. There's some limited ways around that, but that's generally what's going to happen. And there are other types of signals that you can send that are user signals. There's a couple separate ones that are specifically for you to use for whatever purpose you want. That's another type of signal. Okay. All right, so as I said, SIG-child is the one we're going to care the most about, at least for this class. And it happens whenever a child process of a particular parent changes state. And so we're going to be able to capture that. That is generally when we're going to want to do our wait PID for the child to actually find out what happened to the child. What did it just do? Did it end? Did it die abnormally? What happened to it? So we're going to generally see wait PIDs inside of the SIG-child handler. Okay? The first one that we talked about is this program that I'm going to just retype so that you kind of get the feeling, or you actually kind of see what it is kind of in more a little bit slower, so that you can kind of process what's going on. I know a lot of times I've run through code really fast and you go, I've never seen that before, how can I even process it? So I'll try to like slow down a little bit in that sense more often and actually type things out, explain as I'm typing, give you a second to process it, and so forth. Okay? So let's start out. We will write a main function. This is the example I talked about on Monday where you have this model of a dad taking his 5 children to Disneyland, and he lets them all go off and play. They each play for a certain amount of time, and then they come back. In the meantime, dad sleeps. Okay? And I actually said something on Monday that I was very confused about, and I figured out why. It was because I hadn't typed the program in. When I get there, I'll show you what I'm talking about. But in this case, what we're going to do is we're going to start out. So let me put it a little higher on the screen here. There we go. What we're going to do is we're going to start out here, and we're just going to say printf, let my 5 children play while I take a nap. And look, if I was a dad going to Disneyland, I'd be on all the rides too, so I don't know what he's doing, taking the nap. But anyway, that's what this dad is doing. Okay, and then we're going to set up the signal handler by saying signal, sig, C-H-L-D. By the way, the reason they left out all those, they left out letters and things is because it used to be that you had to have a certain file length or a certain name length limitation. And so a lot of these names are really short and kind of leaving out letters just because that's historical in this case. So we are going to tell it what function we need to set as the signal handler. In this case, it's going to be reap child. Okay. And then we're going to start up all these children processes. Okay, so we're just going to go for size t I equals 0, or actually we'll start with 1, so that we just get 1, 2, 3, 4, 5. I is less than or equal to 5, I plus plus. And then we're just going to fork, so we're going to have this kind of, we're not going to actually capture the PID of the child, but in this case we're just going to say if fork equals 0, that means we are the child if we're in this block. We're going to sleep for 3 times the, I guess I said kid before, didn't I? We'll do a kid like this. K-I-D, and then kid, there we go. Sleep for 3 times whatever the kid index is, index starting at 1, right? Sleep in this case is going to emulate playing or whatever, playing at Disneyland. Okay, and then after the child wakes up from the sleep or finishes playing, we're just going to say printf. We're going to say child, and then because we used size t, we have to use like zu or something like that. Is tired, returns to dad, not data, to dad. There we go. I guess it makes sense in computer science. Okay, so there we go, and I might need a parenthesis quote on there. All right, and then we are going to just return 0 from the child. Okay, so that's what's going to happen in the child. We're going to do that 5 times. Boom, 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 and they're going to sleep for 3 seconds, 6 seconds, 9 seconds, etc. Yeah.
Do you not have have the variable there at the end of the printf? Or
Probably. Thank you very much. How about kid? Thank you very much. That would be a bad mistake. Probably would have gotten a warning, I hope. We'll see. Good catch. All right, so anyway, that's going to be the 5 children starting up and just sleeping for a while. Okay, and then we're going to have the parent, in this case like the dad, okay, while num children done playing is less than k num children. Oops. Hang on. Oh no. I knew I'd do something like this. I tried to do a special command, and of course it's not working. Nope. Oh no. Hang on. Match 1 of 76. How about we? No. Oh no. What have I done? Let's try it again. I wonder if any of that got saved. Let's see. We'll find out. I don't think I saved it anyway. Spring. And let's see. It's live. Lecture processing. Let's see. It did get a swap file. Let's see if we can recover it. 5children.c. And Looks like it doesn't want to play. There it goes. Okay. What does it say? It says file swap owned by that. Another program editing the file. I want to recover it. Enter. Okay. Some of it got saved anyway. It looks like most of it did. Okay. Well, anyway. All right. Let's try this again. I won't try to be fancy on this. So we got everything in there for the parent or for the child, and then the parent's going to do while num. Children, what was the name of the variable there? It was num children done playing. Num children done playing is less than k num children. All right, so what are we going to do? We are going to printf at least one child is still playing, so dad nods off. Okay. And then the other day we used, in fact, earlier in this program we used sleep. I don't know if you remember that when I said that, hey, it looks like the dad is waking up, or is not waking up when he should be, and I thought that was because sleep normally stops sleeping at the point where a signal is handled. Actually, or I guess it's not handled. But anyway, it does. If a signal happens, sleep will generally return. What we want to do is we want to actually have the dad not wake up. So we're going to say snooze, which is a little function we wrote that just basically does this and says don't wake up if you get a signal. Okay, so that's what we want to do. We want it to snooze for 5 seconds, and then printf dad wakes up like that, and there we go. And then when you get all the children back, we're just going to say printf all children accounted for. Good job, Dad. All right, something like that. And then we're going to return 0. Okay, so that's our function. Let's run it. Okay, make 5 children. Okay, and when we run this, right, what it does is it does all that forking, and then dad nods off. Child 1 returns after 3 seconds. Dad wakes up. Child 2 and then goes back to sleep. Child 2 and 3 wake up while dad's sleeping in that next 5 seconds, and then dad goes back to sleep again. And then child 4 and 5 also wake up, or return rather, and then that's it. So what did I forget to do? I forgot to write the function that actually does anything, right? So let's see. Now this one I want to delete it. There we go. Okay. So in this case, let's see. Actually, hang on one sec, John. PS. No, it doesn't say it's in there. Anyway. Okay. So we have to actually write reap child. Well, this is going to be a really simple reap child in this case. Okay. All it's going to do, it's going to clean up after the children. So it's going to do wait PID. All right, and then -1 says wait for any child. Okay, null because we don't care about capturing the return values at this point. We're not, you would if you were doing this for a little more robust program. And then 0, which we'll get to changing that today actually, just basically says just block until that child returned, but it's going to have just ended because that's why the signal handler got called. Okay, and then at this point we need to update the num. What was it again? Num children done playing. Okay, and then that should do that. Now, this signal handler is in the parent, and it's getting called when the child ends. Okay, that's how this is getting called. Question? If you didn't write the wait PID there, that's a good question. All that would really happen is it would be as if you were leaking the memory. I mean, you wouldn't clean up after the child. Nothing else would actually happen in that case. It would still actually work. We can test it if you want, but that's it. Any other questions on that? Let's see if this one works now. I just made it. 5 children. There we go. Okay. So same thing again, waiting for 3 seconds, and then returns to dad. Dad wakes up. 2 more children are going to end in the next 5 seconds. And then finally, the last 2 children end, and then dad wakes up, and then we can say that all children are accounted for. Okay, so that's what's happening. The main parent, or the parent function, is in that while loop, but just sleeping for 5 seconds, and the signal handler is happening. And when the dad gets done sleeping, it goes, hey, are all my children back? We're leaving. Question?
So if you didn't
Yes, that's exactly what we did when I didn't write that. The question was, wait, if you didn't write the reap child function, what would happen? The dad would keep waking up, and then that global variable wouldn't be updated, so it would just stay at 0, as it turns out. Yeah. Yeah.
When you call signal sig child, read child, are you giving it like a function pointer to the child, or like what?
Yeah, very good question. When you call the signal function, you are passing in a function pointer to reap child.
Why don't we need to give it the arguments? If we have to.
Good question. Well, you generally don't need to give it arguments. It's a good question, but you don't need to. When you say signal, all it needs to know is reap child. There's only one argument that reap child must take, and it happens to be an integer for the signal number, which is it. Yeah, good question. Yeah, Brenda.
Why does cleaning up after the children make the dad stop cycling?
Cleaning up after the children does not do that. I mean, the good question, like you're saying, well, why does cleaning up after the children make it happen? It's this that makes the dad, because it's a global variable that is being updated by the signal handler. All right. Now, if you're thinking, wait a minute, I thought children and parents have different memories, and so if I update the global variable here, it's not going to update in the parent. Remember, it's not none of these. This function is not happening in the child. This function is happening in the parent when the child ends. So it, in fact, is the same global variable. Okay? All right. So that's what happens here. What if I guess I'll just change it here. What if we change something and say, let's let all the children sleep for the same amount of time? Okay? So in other words, they're all going to go out and play, and they're all going to come back at the exact same amount of time. Let's find out what happens if we do this. 5 children. Okay, so now same thing's going to happen. They all come back at the same time, maybe in some other different order, right? Dad wakes up, and then 5 seconds later, Dad wakes up again, and we got all the children back, but somehow num children done must not have been updated correctly. Okay, let's actually see what happens. Let's look at this again, like this. Let's do this. In the handler, let's just do this. Printf num children done playing, like that. And let's see, that should do it. And it is going to be num. I'm going to try this again. Ah, that time it worked. Whew. Okay. All right. And then that should do it. Okay. So, no. 5 children. There we go. All right. And so let's see what happens. Oh, well, it looks like 4 of them seem to have come back all at once and called that signal handler once. It turns out that if children end at roughly the same time, this is, by the way, this is a kernel race condition, and this is how the kernel handles it. If a bunch of children end at the same time, the kernel will just say, fine, I am going to call one instance of the child handler function. You get to deal with whether or not, like the ramifications of that is. Okay, so it's kind of a race condition in the sense that, in this case, 4 of them were handled by only one child handler process, like happening at the same time. The nice thing about it is that if you are already in the signal handler and another child ends, it will call the signal handler again. So it's not that you lose any children, it's just that you have to deal with all the ones that have ended already immediately. Okay, and you have to do that inside the child handler. We'll see how that goes. Yeah, question?
Just to make sure I get what you just said.
Mm-hmm.
It's not that children are interrupting each other before it's incremented. It's that they're coming in at the same time, and the kernel says, run it once, increment it once. It's not like they're...
Exactly. So the comment, it's a perfect comment. The comment was, it's not that the children are ending and not being processed and like the signal handler is not getting called for them. It's that they're all coming in at the same time. The function is only getting called once, and therefore, and they've already ended, and that function only ends up incrementing num children done once. What we can do is we can modify our program to actually say, oh, all right, well, maybe if all those children have ended when the signal handler happens, let's do this. While true, inside our signal handler. Okay, I'm going to get rid of this for now, just so because we don't need that one right now. Okay, when the while true, okay, what we're going to do is we're going to wait for all of the children. Okay, and if the return value for wait PID, which normally is the child that was just waited for, if it returns negative, or if it returns -1, or I guess a negative number, it means that there are no more children waiting in that one-like thing. Now, if another one happens to end, it will call the signal handler again. Okay, so it's not like you have to kind of keep waiting and maybe it's happened. There's no more race conditions in that case. Okay, so what you need to do in this case is you need to say, oh, all right, we better capture the PID for this, right? And if PID is less than 0, we're just going to return. Okay, so we're basically going to break out of the while loop after we've now handled all of the potential children that may have ended in that case. Okay, question? Yeah.
So why is the PID less than 1 for the last child?
It's not less than 1 for the last child. It's that we're recalling. We're going to call wait PID again. There are no more children that have to end. Therefore, wait PID says there's no more children that have ended now. Therefore, we are going to return.
Why would that help? Why would that help? Like, how will that make it?
This will for every child that's ended in this little loop here, right? It's going to stay in that loop until it says no more children are left. That's what's happening here. You not get that? If they finish at the same time, that's okay, but then we've got a while loop that's going to get the first one, then the second one, then the third one, then the fourth one, and it's going to keep going in the while loop and just keep asking. And one of them will end up being the one that the wait PID captures. We don't know which one, but one of them will. Then we'll go through the while loop again, and it will return a PID. So we'll go, oh, we're not going to break. We're then going to go do it again, and do it again, and do it again until all of the children are captured. Okay? Still don't get it. You have a question about it? Go ahead. Think of a question. Yeah.
So read child is getting called once, but that doesn't necessarily. But wait PID is getting called multiple times until all of the children have been taken care of.
Yes, wait PID is getting called. Well, wait PID is getting called once when any child ends, right. And then we're going into this while loop saying, oh, let's keep waiting for children until there are no more left. Okay, and then we're going to end. Okay. Question in the back. Yeah.
Does wait PID stop after all the children are done, or all the children that were called as part of this one rechild?
That is a good question. In this case, the way we're running it right now, it blocks while there are still children not done. So it will wait. Yeah, it'll actually wait for all of them to be done. Now, they're all going to come back in roughly the same amount of time in this case, but that's a good point, and we'll see how to handle that in a second if you want to deal with it differently. Hosmer, you have a question? Yeah, okay. All right. Okay. If you're still, well, let's see what happens when we run this. And okay, 5 children. Okay. Now it's going to go into that while loop. They're going to return to dad. All 5 of them end up getting captured in that while loop, and then dad wakes up, and it did increment all 5 of. It incremented num children done each time. Yeah.
So how many times is the signal handler called?
Yeah, very good question. In this case, the signal handler. It turns out that the signal handler is called once, as it turns out. It may get called again. Although it doesn't matter. It doesn't actually matter because we're calling wait PID. Remember what wait PID does, and this is a very good point. In this form, when we say wait PID like this, when we say wait PID like that, what it says is, okay, wait for any child to finish if there are outstanding children to finish. Like if there's any children out there, wait for any one of them to finish. Okay? And it will actually block until a child finishes. If there are no more children, because they're all already finished, it will return -1 immediately, and that's when we'll break out of that loop. Carl.
So to be clear here, if you switch back the sleep statement there, the sleep 3 times kid,
Yeah.
would we never get the printed statement about the dad? Like
Yeah, let's do that. So Khaled says, whoa, wait a minute. What if we made the following change and just said, oh, let's see if our new method, which we proved works for the one where they're all ending at the same time, what if we did this now? What's going to happen? And his comment was, oh, is it going to mean that we're never going to, we're not going to see all that dad wakes up business until way at the end? Let's find out. Okay. All right, now the child's playing. Remember, now they're doing 3 seconds each, right? Okay, child 1 returned after 3 seconds. Child 2 returned after 3 seconds. Dad still hasn't woken up yet. Child 3 returned. Child 4 returned. Dad still hasn't woken up. In fact, Dad's trying to wake up, but guess what? The signal handler is the part of the program that's running. It will not also, it's only one process now. Even though there's 2 functions that could happen, the signal handler is the one that's in this while loop, and the dad never has a chance to actually wake up and see if the children have ended yet. So yes, we broke this one by doing that fancy while loop. Oh, we got to do something else. Yeah.
And so when it's running, when the signal handler is running, it's running for the first child that returned. It's like running on the call of the first child.
Yeah, the question is the signal handler running on the call of when the first child ends? It could be the first, or in this case it is the first, because they are ending at different times. It could be many ending at the same time, calling at once. But in this case, yes. The signal handler starts when the first child finishes, and then it never leaves the signal handler until all of them finish. This is actually not good programming. You want your signal handler to be fast. If you did 107E, you know that's true about interrupts. This is basically the same sort of thing. You want your signal handler to be in and out as fast as you can. So you don't want to wait for all those other children. Remember, the dad had a job to do. The dad was supposed to wake up and say, oh, I'm going to see if all my children are back. But he couldn't until all the children got back. Right? So that's the big problem there. Yeah?
Has the first child actually ended when the signal handler is called, or is it just right before it's ended? Because otherwise, wouldn't the wait PID not be able to capture the first child?
No. Good question. Is the wait PID called before or after the child ends? It is called because the child has ended. Okay? So, in other words, reap child gets called when the child has ended, and it has not been cleaned up yet. There's no wait. So the operating system is basically saying, oh, this child has ended. Well, I'm going to wait around until somebody cleans it up, until the parent cleans it up. And so it's in the process of being finished, but the child hasn't been cleaned up yet. That's why it gets the PID returned at that point. Yeah, question?
So if we have known kids on the line, does it have 5?
If we print it out here, yeah, let's see what happens when we do that. All right, what it's going to do, it's going to, when each child gets back, it's going to just do that, right? Because, by the way, it's still inside the loop, right? It's still inside that while loop, not leaving that while loop. I'll show it to you again, and then we'll see. We'll let it finish here, and then we'll see. There we go. Okay, so it's still in this while loop. Remember, forever, true, while true, it's in that while loop until wait PID returns a negative number saying there are no more children left. And in this case, that's really not what we'd like to do. It's not the best coding style because we're staying in that signal handler until they all finish. What if one was supposed to go on for days? Well, the rest of the program wouldn't be able to do anything. So you shouldn't stay in the signal handler that long. Yeah.
But when the other children that is waiting for it to return, when they do return, does it call read child again because the signal sent again?
Yeah, this is a good question. When I believe it does, as it turns out, call reap child again. Yeah, I mean, let's do that. Let's find out. Let's see if we can test this. I'm not 100% sure this is going to do anything, but let's test this. Reap child just called. Okay. The question was, what happens if they've been cleaned up in here? Does another signal get generated? I believe it will. I'm not 100% sure. Once it's cleaned up, it might be removed from it probably is. It's probably once it's cleaned up, it goes, oh, I don't need to send another signal because it's been cleaned up. I'm guessing that's the case. But let's just find out. Okay, let's see how many times this. So what we actually need to do here is we also need to, let's say all children are accounted for. Let's just see if there's any other issues maybe down here later. So let's do another snooze for like 3 more seconds or something like that. Okay, make 5 children. Okay, so Boom, reap child just got called. Now it's going to be in reap child, not calling it again until all 5 get done. We know because it's in that while loop, and it's just going to sit there and do that. Okay, and it doesn't. You can't call the same signal from inside the. There it goes again. It did get called again. So yeah, it looks like it got called for once more because all those children that triggered it. So I was wrong. It does get called at least one more time. Now it didn't matter because it would go into that while loop and it would immediately say, "There's no more children. Goodbye," and that's it. So there's some logic there you have to handle. Yeah.
Does the sig parameter in reap child not have any information about how many children were clumped together?
Good question. The signal parameter, I'm going to get rid of some of these things because we're going to change it again in a second. The signal here, over here, that parameter, all it says in this case is that it's a sig child. That's the only thing it gives you. It doesn't give you any other information. It just says which signal. You could ask which signal got called. I mean, you basically look at that and go, oh, is it the sig child? Yes. That's it. Maybe we want this to be an encompassing function to capture many signals. And maybe you want to know which signal actually triggered it. So that's how you do that. Yeah, Bryn?
So in this case, aren't all the child processes not created yet? But the reap child is called at the start. So do we just like pause it?
Be careful. Do you mean reap child's called right here?
Oh, so
It is not called there. This is just simply calling signal with a function pointer to reap child, saying that when a child ends, that's when reap child gets called.
well, when the first one ends, the rest of them still haven't been created, right?
That's a good question. It may be the case that the rest of them haven't been created yet. By the time, you're right, in this for loop here, if we had made it sleep 0 or no sleep at all, then it might have jumped into the loop and then it would have done it. But it still would have worked okay because let's say it didn't have any children at that point. It would have exited the reap child, but then the next child would have gotten created and it would have gone back and called. So, I mean, it's not like anything would have broken in that case. But you're right. It could have been that we ended up in reap child before any of the other children were created. But it's still going to get called later when they do get created and then eventually finish. Good. Lots of good questions here. I'm glad I'm going over this again, or at least this part of it here. Okay. So what do we want to do in this case? So now we've got this problem here. Remember, we've changed the behavior by adding this while loop up here. Okay, we've said, wait, block until all the children are done. And if we've got 5 children outstanding, then it's going to sit there and block until all the children are done. And that's not what we want. We want the signal handler to be in and out really quickly. That's the basic idea. So it turns out that we will finally get a chance to use this final parameter for wait PID. Okay, this parameter, there's a bunch of flags you can put in there. You just OR them together. One of the flags that we care about, and in fact specifically for this, is called W no hang. And W no hang is a flag that says, wait for any child, except if there are none that are finished, just return immediately with a return value of 0. So that means a return value of 0 means that there are children remaining that have not ended yet, but I'm going to return now because I don't want to block on this. I don't want to stick around waiting for those in this while loop. So the only other thing we have to change here is we have to say, oh, fine, if PID is less than or equal to 0, because if the 0 case, there are still children, but they're still going, so I'm not going to stick around and try to wait for them. I'm going to come back later when they finish and call this function. That's what's going on here. So let's try this and see if it works. 5 children. Okay, 5 children. So remember, now we've got this idea where we want the dad to wake back up after the first 2 children. Oh, we got the reap children. I'll take that out so you can see what's going on in a second here. But you can see that Dad's waking up now, which is exactly what we wanted, which is exactly what we had in the very first one. But now we're doing it in a way that we can capture in case some children end at exactly the same time, or roughly the same time. Okay, let me just run it again without this line in there anymore. And we'll just see it work in general. What questions do you have about this? The purpose of W no hang. And we will use that very often. Okay? And we'll use that specifically because we want to keep our program going. We don't want to sit there and go, oh, let's wait for the child. Oh, let's wait around for the child. Let's do something else. Let the signal handler get called when the child ends and deal with it at that point. Question?
So basically the flag just says, don't stop the deal with any children that have already ended. Whereas if we didn't have the flag, we would just wait until something.
Yeah, so the question is, this flag, or the comment is, this flag W no hang, it says to the wait PID function, if there is a child that's ended, return that PID and clean it up. If any of the children have ended, take one of them, clean it up, and give me that PID back so I can do whatever else I want with it. If there are no children that have ended, but there are still children out there, don't wait for one like we've always done in the past. Just return 0 and say, look, they're still there, but I'm not going to wait. You asked me not to wait for them. That's what it's doing. Question?
Can you call this like 10 minutes after the process dies? Like, is there like a queue somewhere of processes that need to be cleaned up?
So the question is there a queue of processes that needs to be cleaned up? Yes. I mean, it's operating system specific, and I don't know exactly how Linux does it, but the operating system is part of this whole game. When the child ends, the operating system says, oh, okay, I owe the parent a signal, and it sends the signal whenever that child ends. Now, if the parent has already ended, well then, you don't want that. But in this case, the parent, we've made it so the parent will not end until all the children end. But yeah, that's kind of what's happening. The operating system is saying, I'm going to build up a little queue of ended children, and then I'll call wait PID when I need to. Yeah. Lots of other questions. Yeah.
So is reach-out called 2 times only, or is it 5?
Good question. We don't know how many times reap child is called in general. In this case, because they're staggered 3 seconds, 3 seconds, 3 seconds, 3 seconds, it's called 5 times because there aren't 2 that end at the same time. Anytime 2 or more will end at the same time, it could only get called once. And that's why you have to handle them all inside that, because you may not get another call later. And it's just a race condition that's kind of built into the operating system. And this is the way they've said, look, you have to plan for if reap child gets called, maybe more than one child has ended, you better deal with that. Because we're not going to call it again in that case. Yeah.
So if we do go back to when multiple, say like 2 can finish at the same time.
When 2 can finish at the same time, yeah.
Then this would only get called once for those 2. And you get 2 PIDs, like you go through the while loop twice and then be done.
Correct. You would go through so yes, if 2 ended at the same time, you would end up getting called once, probably, and then it would go, then this while loop here would go through both of them and clean both of them up, and then find out that none of the others have finished, return 0, and then you return from the function. Yep.
What is null used for?
Null in this case, remember this was the status, so we could have done, in fact you normally should do something like this, status, and then you paste in status like that, and it gives you more information. What was the return value of the child? Did it end abnormally? Was there there's lots of information some more information you can get from that. What status did it? How did it end? Was it stopped, or rather, did it end, or was it stopped, or was it continued? That gives you more information about that. Good questions. Yeah?
Could you run this without the 3 times kids instead of just sleep 3?
Could I run it without which?
So now you have to sleep 3 times kids.
Oh, yeah, you want me to run it without so they all end at the same time?
Yeah.
Sure. Let's see. So if they all end at the same time, I'm going to do that. And let's see. Okay, so remember, they're all going to go boom and end after 3 seconds or whatever. Right? Boom, they all ended. Dad finally wakes up and says, oh, they've all ended, we're done. And they got handled inside that. Good question. Right. That's a lot of like stuff packed into one program, a lot of different things going on. But what we've learned now is, well, these signal handlers have some nuance to them. They have this ability to get called, but sometimes it's a little bit like odd because 2 things could kind of call it at the same time. So that's nuanced. We've got wait PID, which will wait for any children, and you can use -1 for the first parameter to wait for any of the children. And now we've said, yeah, but what if we don't want you to block and wait for that child? We want you to just return immediately. And we capture the information about that, saying, oh, there's no, if it's 0, there are children still remaining that have not been captured yet. Okay. Now, we didn't care if it was children still remaining or all the children are done, because we just know that we're counting correctly. So reap child will get called again if we haven't counted, or if all the children are still remaining, just because the parent program or the parent part of the process is kind of doing its own thing. Okay. All right. I know there's a lot going on there, but do ask more questions, and feel free to go run the code yourself if you want to. You can download it. I didn't put it in the slideshow today. I'm not sure if that screwed up my tablet or not, but the other day. But I'll try that again in the future. So anyway, we went through all of these different cases. So I don't think we need to redo these, because we did them kind of as we go along. But feel free to read the slides about that. It's just basically going through exactly what we did live. And you saw that we had some various cases where we needed to do more logic and different type of logic. Okay. All right. So let's see. That, I think, is that for there. There are other flags besides W no hang. There's also W untraced, which is a weird name, but basically what it means is block until a child process has either ended or been stopped. And stopped is paused, not ended. And we'll see lots of cases where they get paused. If you use W untraced with W no hang, it removes that blocking part. It doesn't actually block in that case. W no hang always says, well, I'm not going to block. But the other ones, W untraced is if it stops. And then you also have W continued for the situation where the child process has been stopped and then gets started back up again. Your parent will also get a notice about that, get a signal about that. Okay? So often we will see three of them together, W untraced or W continued or W no hang. And that just says, look, I want you to wait and return information about a child process that has changed any kind of its state, not just ended, not just not just stopped, not just continued. And by the way, don't actually block when you're doing that. Okay? All right. So that's the basic idea of signal handlers so far. We have some more nuance in race conditions that we have to deal with going forward. Okay? So we have to talk about some more synchronization issues. Okay? When you talk about signal handlers, okay, remember that the signal handler gets called when the whatever thing happens. Okay? So the question came up earlier and somebody said, what if the child process ends before the parent actually gets to something or whatever? That could happen. All right? And because of the way you write your code, that might actually happen, and it might not be what you want. Or at least what happens might not be what you want. So we have to actually deal with this. Here's what we're going to do. I'm going to write another program, and it's going to be basically a job list sort of program. In other words, we're going to start up a bunch of programs using fork exec CVP, like we've done before. We're going to start them up, and we're going to add them to a job list. Now, in fact, you're going to do this for assignment 4, coming up not this week, but next week. You're going to do this coming up for that assignment. And you're going to have to do this because your shell does that. Whenever you type a command, guess what? The shell takes that command and puts it into some list that it's keeping track of to know which programs are running. That's what it's doing. So that's what we're going to do. We're going to run these programs, 3 of them as it turns out. And then we're going to, every second, by the way, we're going to do it 1 second after the other. And then we're going to have a signal handler that gets called when the child's state changes. Remember, it always gets called when the child's state changes. And we are going to add it to this job list through the signal handler. Okay? All right. And then the parent is also going to maintain, it's kind of the parent is maintaining this job list is really what it is. Okay, in fact, we're not really maintaining it all, we're just printing it out. Okay, let me show you the program, and then we will see it in action. Okay, this is going to be called job list synchronization.c, and it's going to be the following. Again, we'll write the main part first, just to kind of show you what it's actually doing here. Okay, I'm going to call, by the way, the date function. If you haven't seen the date function before, it just does the date, just prints out the date. Okay, so I'm going to call the date function, and it's going to run that and then print it out to the screen. Okay, that's all the date function is actually going to do. Okay, and so what we're going to do is we're going to set up a signal handler, signal sig child, and it's going to be in this case reap processes. All right, that's setting up the signal handler. Okay, and then we are going to do what we call we're going to just actually we're going to do this in a minute. Right now we're just going to start the actual for loop to start the processes. So for size t I equals 0, I is less than 3 in this case, I plus plus. Okay, PID t PID equals fork. Okay, if I don't know why this is not. Okay, there. Anyway, all right, fork. I might have had a mistake in there somewhere. Well, anyway, if the PID is 0, means we're in the child. Okay, what are we going to do in there in this case? We are actually going to just call execvp. Okay, and it's k arguments 0 and k arguments. Remember, this is how execvp works. Okay, and that's that. Okay, remember that will not return if it works, and we're going to assume the date function is going to work in this case. We're not doing any error checking in that case. Okay, and then we're going to sleep for 1 second. Okay, which basically forces the CPU, or forces the parent off the CPU. What do I mean by that? I mean that it's going to tell the parent, go to sleep, and then the child is actually going to get to do its thing. If you have multiple processors, this will probably happen anyway. But in this case, we're just forcing it to make the parent wait for a second. Why? Well, who knows? Maybe this is a system where you're typing commands in and it's waiting for commands to come. Whatever. For now, we're just forcing it off the CPU, and then we're going to print job %d added to the job list, and we're going to print the actual PID of the child. Okay. And then we're going to return 0, and that's that. Okay, so everybody gets what's going on here. We're going to start a process, 3 processes, the date command. We're going to print out, hey, I've started these processes after 1 second. Okay, that's what's happening there. In reap processes in this case, okay, what we're going to do is we're still going to do this while true, because we don't know, we're almost always going to do this from now on, because we don't know how many children have ended or have changed state, okay? And we're going to say PID equals wait PID, -1 null, and W no hang, because we don't want to wait, we don't want to block on these, okay? And then we're going to say if PID is less or equal to 0, we're simply going to break, same exact things we did before, okay? And then now we're going to, if we were keeping track of this, which you'll do for assignment 4, we're going to print job %, we're just going to print it in this case, %d removed from the job list. Okay, so in this case, what it's going to do is when the job ends, remember no hang, actually in this case it's just when the job actually finishes, okay, it will say it's removed from the job list. When the child ends, well, why are we keeping it in the job list? Let's remove it from the job list. Okay, so again, the parent is creating all these processes and putting it into the job list. We're just printing it out, but it's like putting it into a job list. When the signal handler gets called for the child process, it says, "Oh, the job is now removed from the job list." Okay, let's run this and see what happens. Okay, job list synchronization. All right, it says job 23735, which is the PID of the child, removed from the job list. And then it says job 23735 added to the job list. And then it says the date. Great. Or actually it said the date first, in fact, because it said the date and then ended. And then it did the same thing, and then it says the next job was removed and then added, and then removed and then added. Now, you're probably saying to yourself, well, that's kind of dumb. The job lists here, they're being removed before they're being added, right? And you've got to say to yourself, well, why is that happening, right? Well, what did we do to make it happen? That's the bigger question. Yeah, comment or question?
I was just wondering, is that because we like force the parent off the CPU?
Yeah, we did this little sleep for 1 second, right? Well, when by the time it gets to that sleep, the child is already on its way, and the date does not take more than 1 second to happen. It happens like instantly, right? When the date function is done, command is done, it calls the signal handler. All of that happens before 1 second is done. Now, you'll notice when I run it that 1 second actually doesn't happen by the time it says. It's because sleep does not wait that 1 second. If I changed to snooze, it would actually wait 1 second. But in this case, it just wakes up immediately in that case. Hasn't it?
If you remove the sleep, wouldn't it also sometimes run into the issue because exec CDP would automatically return child and then you would.
Yeah, very good question, very good comment. The question and comment was, wait. If we remove sleep 1, wouldn't it still have this potential problem? Because you don't know if the date command is going to run faster than this command is going to get to. Absolutely. Like you don't know that. And then we're purposely putting in this sleep in here to say, hey, this is something that could happen even though we're forcing it to, so we know it's going to happen because we're forcing it to. But yeah, these are race conditions. You can't predict them. Very good point. Okay. Yeah.
So if you had the print, like that the PID was added to the list before you checked if it was the child, what would happen?
If you had this right here before you checked if it was the child, it would remember that it would get printed twice in that case because the child and the parent would do it. So that's not really what we wanted to do in this case. But you see the issue here. We've got this race condition, and really what we want to do is we want the child not to send that signal until after this command. That's what we want. Okay, we want the child to, maybe it ends. We don't care if the child ends. We just don't want that signal to be sent until we're ready for that signal to be sent. Okay, and in this case, it's going to be after we've added the job to the list, because that would be kind of hard. This is especially true if you literally were keeping some list that you needed to, like if it was a queue or something, or some set or something of like the list, and you tried to remove it before you added it. Well, you're going to crash, right? Or there's some other like, oh, I can't remove that job even though it ended. That's weird, right? So you need to somehow be able to say, don't call that signal until after this printf in this case. All right, so how are we going to do that? Okay, there's the thing we just did. What we need to do, okay, well, we actually kind of went through all this detail here. What we need to do is we need to use a different type of system call here. Okay, we need to have this idea of a signal set, and this signal set is going to be a data structure that says when you call this function called sigprocmask, that says don't let a particular signal get called until we unblock it. Okay, so we're going to block some signal. In fact, sometimes you can block as many signals as you want. But we're going to, in particular, block the sig child until we're ready for that sig child to be okay to be fired. That's all we're doing. Okay, there's 3 different functions we have to deal with in this case. The one is called sig empty set. Let me make this a little bigger. One is called sig empty set, and sig empty set basically takes this sig set t type that we have, and it kind of initializes it and says there are no signals in that set. Okay, it's just an initialization. And by the way, this signal set, it's basically an integer that's got a bunch of bits. That's obviously it's got a bunch of bits in it. The bits are set depending on the signal. And it's a 32-bit integer. It turns out there's less than 32 signals, so we can get away with that. Then, if you want to add a particular signal to a set, you say, okay, I'm going to pass in the set that I'm going to add, and then I'm going to tell it which signal I want to actually add to that set. Okay, you can also remove them. The 3 that we're going to care about right now are these 3. And then, if you want to say, go block this signal, you call sigprocmask with a value called sigblock, and then you pass in the sig set that you care about. You can also get back the signal that you that have already been set. Like it's kind of one of those weird things where they're like, well, we're not going to tell you. Remember, like from day one where we talked about UMask, and there was that weird thing where the only way to check UMask was to actually change it, and you get back what you checked. It's the same sort of thing here. Why they did this is just historical, I'm guessing. But anyway, most of the time we're not going to care about the existing set. We're just going to say, look, here's our new set. I don't care what signals are already done. Let's just go with it. If you're writing a more robust program, you might care about that. Okay? All right, so let's see how this actually works in practice. So let's go modify our main function here. We're not going to have to do anything, by the way, to the reap processes. We're just going to have to change main here to have this signal set that we're going to block, and you'll see how that happens. Okay? All right. So what we're going to do is we're going to, same thing, we're going to set up this signal, and then we are going to say, okay, fine. I'm going to get a sig set underscore t, and I'm just going to call it my set. I'm going to initialize it by calling sig empty set, and then we pass in a pointer to the set, and then we say, let's add the sig child to that. Sig add set, set, and sig chld. Okay. All right. So at this point, now we've got our set that we're going to be able to say, hey, wait for this signal, like block this signal until we're ready for it. Okay. We don't need to quite block it yet, right? We want to block it before we actually have the chance to call it, like before we actually do fork, because at that point we need it to be blocked. Okay, so at this point we're going to say sig proc mask, okay, sig block, and then we are going to pass in our set, and we're not going to care about the other set. So at this point, right before fork, we have blocked the signals. It turns out, and this is a good thing as it turns out, blocked signals are passed along to your children. Whatever signals are blocked in the parent are also blocked in the children. And the reason for that is so that we can do this. I mean, that's really the main reason that we did this, is so that we can do that. So by the time you get to this child part, by the time we actually run the date command, we are not allowed, in fact, the program is not allowed to call the sig child signal. Now, it doesn't mean that it gets ignored forever. If once we unblock the signals, that queue of signals that need to be sent will go, oh, okay, the operating system will go, oh, great, I've got this child that's ended, I'd better call it. But it's only after we unblock it. Okay? All right. So what do we have to do at this point? We now need to, in the child, this is going to seem a little strange, but in the child, we're going to do sig proc mask. Okay? Actually, I kind of lied to you a little bit earlier. The reason the signals get blocked in the children is not because of this, actually. It's because you may want the children to also be able to block on their signal, and it might be because you're running the same sort of program. We will see why that's actually not important because of what I'm exactly going to do right now. We're going to unblock for the child only, right there. So in other words, what if date called the child process? If we didn't unblock at that point, the date function would start out with its child process blocked. And date doesn't do that, so it doesn't actually matter that much. But if date had its own child, because the signal sets are passed along to their children, date would also have that issue, and it might not be able to handle that. Okay, so who knows? That might be an issue. But for now, what we're doing is we're saying in the child, go ahead and unblock because it doesn't matter. The child, we don't care if the child gets a child handler called. We care about the parent's child handler getting called, and we don't want it to unblock until right here after the printf. Okay, so after the printf, sig proc mask sig unblock in the parent set. We don't care about what the previous one was. No, like that. After this, now when the child the parent's signal handler can get called when the child ends, it probably already will have ended because we just waited for a whole second. And in this case, it's a really fast function. Question?
Can you explain again why calling the unblock inside the child doesn't unblock?
Yes. Good, very good question. The question, wait, go back a second and explain why unblocking the signal in the child doesn't have anything to do with the parent. Okay. The parent, forget about the child for a second. The parent has a main function and it has a signal handler for the SIG child. The parent's SIG child handler gets called when the child ends, unless we have told the parent we're not going to let you accept that signal. Really what it is, or you can't send that signal to the parent. Okay? So it doesn't matter if the child's signal is blocked or not. That's dealing with its own children if it had some. So it doesn't matter. So when you say SIG proc mask, SIG unblock inside the child, it's just saying I'm making sure the child doesn't have any signals of its own blocked right now. Okay? And that might be important to the child, right? In the parent though, even here we are still blocking that signal for the parent because the last thing the parent saw was this block right here before it forked. So the parent's child handler is not going to get called until line 45 down here when we call unblock. We'd say SIG proc mask unblock, SIG unblock on that set. At that point, now the parent's signal handler can get called. And it will get called because the operating system goes, oh, now you're accepting signals? I've got one for you. And it calls it then. Hopefully, this will actually see how this works, jobless synchronization. And hopefully, there we go. Now we actually are waiting for 1 second. And now the jobs are added and then removed in the proper order. Why? Because we didn't allow them to be removed until they've been added. And in this case, that just took us a little time to add it. And that's the way it goes. Okay? Question?
But the date still gets printed before you add the job.
Yeah, the date gets printed before we add the job. We don't really care about that because we've said that's a good point though. We said, hey, go run, right? We're trying to do our own adding and we're trying to do our own bookkeeping, but yeah, you're off and running. Right? Now, if you want to do that, yeah, you wouldn't. If you needed to do that, we would have done something like this. If you said, wait, I don't even want date to run before we did the exec CVP, right? We would have to, before we even forked, we would have to then figure out how to do that. Now, this also might be an issue. You can't. In this case, we would have to do something else to try to figure out how to wait to print until the parent has done it. But once you've got a child and a parent, they're kind of independent anyway. So you're not really going to want to, you're not going to be able to wait for the parent on the child. The child is not really going to be able to wait for the parent itself. So you've got to be able to figure some other logic out to do that. Yeah.
One more.
Yeah.
The same way that SIG proc mask and everything is passed down to the children, is the signal handler also passed down? So say if they had a child process and that ended, would read processes be called on that?
Very good question. The question was, wait, is reap processes also passed down to the child? It certainly is because it's part of the program, right? So the child has access to all its own functions. Now, the child's reap process won't get called when the child ends because it doesn't have a child that's ended. That was a bit Inception-like.
Earlier, how date might have a child process?
Yeah, right. The date might have a child process, in which case, then it would get called.
And in that case, we would have more job removed than job added. Because we never did a job added.
Yeah. So the question was, wait. If the date did have a child, then this signal might get called. Now, likely, the child would set up its own. Well, actually, that's a good point. In this case, this one would it might have gotten called if the child process had a child process. Yeah. If the child process had a child process. Yeah, the child's one would get called. It wouldn't get added to the parent's job list. It would get added to the child's job list. Or I guess it would get removed from the child's job list. So you would have to put more logic in there if you cared about that. Yeah, good point. Yeah. What you could also do is you can basically say you can set up the signal. You can say signal with a null value. Well, basically it's saying don't handle it anymore. You could do that in the child if you cared about that. We happen to not care about that for this part. Very good point. There are lots of things to think about with these things when you're building these real programs. Yep.
So sig block, does that not allow the program to receive signals or send signals?
It does not allow. Good question. The question was, does sig block not allow the program to receive signals or send it? It doesn't allow the parent in this case to receive that signal. Its signal handler will not get called. It may be queued up to get called later, but it will not get called. Yeah, good question. Yeah.
I was going to ask, is there a limit to how many signals the operating system will block and store?
Oh, good question. Is there some list or some queue limit on the number of signals? I don't know of any. It's probably big enough that it's not going to matter. Like it's probably thousands, and you probably likely won't be able to even create thousands of children anyway or whatever. So it's probably some limit that we aren't going to worry about. Yeah, good question.
If we comment out the block and the child, it should still run the same, right?
If we commented this out, it's going to run exactly the same because the child isn't going to get any children, and it's not going to matter anyway. Although, if we ran another program that had children, yeah, it probably would print that some job has been added. And like, well, that's weird. Why did that happen, right? But no, in this case, not going to matter. Did I delete the wrong one? Oh no, thank you for. Oh, you want to do this one? That one would just make you behave as it did before. That one. Thank you. All right, jobless synchronization. Yeah, same sort of thing. Right? No children for the children are calling that function.
But if you had one that did,
if you had one that did.
Had a function that did.
Right. If date had its own child process, yeah, we probably would have gotten a weird printf in there that said some other process had been added to the job list. And we're going, well. So again, when you're trying to do these things, you have to kind of keep track of some of the details of these because it's tricky. Yeah. Good question. Yeah.
Is there a way to remove the connection between the function pointer and the signal?
Yeah, good question. If you want to say stop calling my function or signal handler, I forget exactly what it is, but it's another. You basically do signal, and then instead of sig child, it's like no signal, or it's not that, but it's something like that. I don't remember exactly what it is, but that's what it is. In fact, we can look it up. If we do man signal, let's see. Here we go. Let's see. Sig. Here we go. Sig IGN means the signal is going to get ignored, or sig DFL means that the default action will happen. So you just pass that into signal, and it goes, oh, all right. No more sig child is going to be called in my process. Yeah, good question. All right. Kind of nice when you have the manual right there, your fingertips. Okay. All right. So that's those are the signals there. We have gone through the different types of signals. We can actually write a little function to kind of capture this instead of writing each little part out individually. In this case, we could write impose sig child block, which sets up a set and then calls sig procmask to block. And then we could do the exact lift one, which does the same sort of thing except unblocks it. You could also have one that toggles it if you want to, and you'll see those functions. We've written some of those functions for you there. Okay. All right. We already did this, the improved job list. And what else can we say for it? Yeah, as I said, forked process inherits the block signal sets. So it should lift that signal just in case the child cares about it. And as people have already mentioned, it probably should also it should get rid of that signal handler too, so it doesn't get called when the child ends, because that's not part of our program. So again, things you have to think about when you're building these for real. You have to do lots and lots of testing on this sort of stuff. Okay, two more quick system calls here. Processes can send messages to other processes without something happening. You are allowed to send a signal to another process. You do it using a slightly ill-defined command called kill. Now, kill was named because the only signal that they originally sent was one to terminate a process. basically said kill this process, and it means not make it stop running. Right? So that was the original. And then they said, well, what if we want to send other signals? Let's just keep kill. Why didn't we call it send signal or something? I don't know. But they kept it as called kill. Okay, so it doesn't actually kill. If you send a sig kill, yes, it will terminate the process. But otherwise, you are allowed to give a PID, send a particular signal. Okay, so if you want to send the sig child signal to a particular process, you can send it. You can also send, I think there's two other ones called it's SIG USR1, which is like a generic one that you're allowed to send. Just because, hey, maybe you want to send one that's not a special one that says kill or that says that says stop or that says continue or whatever. We will see lots of use of these as we go. You can also send a signal to yourself, which is you do by the raise system call, which basically just takes the signal number you're trying and it sends it to your own process. It is exactly like saying kill with get PID for your own PID signal number. You could use either, and they're interchangeable. Okay. You can also get the value of, or you can change PID to not be the actual PID. You can make it affect other processes that are tangentially related to a particular process. And you handle that with a thing called groups, which I'm not going to go into right now. But if you send a negative number less than 1 to kill, it actually goes and finds the group that's associated with that process. What you can do with processes, you can set them up such they're in same groups. So if you want to send a signal to one process, it can then, if you want to send one kill signal, it can go to a whole bunch of different processes. So it's nice to have these groups. We'll get into groups when you get to assignment 4. And then you can also be 0 or -1. We're not going to worry about that for right now. Okay, that was a lot of stuff. You have assignment 2 due tomorrow. Assignment 3 will come out tomorrow morning. I'll release it first thing in the morning for anybody who wants to get going on it. And I will explain a little bit about assignment 3 on Monday. So if you want to get started on it, maybe I'll do a little video. I don't know when I'm going to do a little video. But anyway, I will do some explaining about assignment 3 on Monday. All right, last minute questions on this stuff or otherwise? Yeah.
What's assignment 3 going to be due?
Assignment 3 is actually going to be due a week from Sunday. So it's a little longer amount of time. And then the next one's going to be out that day. And then the midterm happens, so you've got an extra time for the next one as well. So it's a little stretched out because midterms and so forth. All right, see you guys Monday. We're in lab. Oh, that reminds me. I totally forgot. Sorry, one last thing. There are a lot of people who wanted to do the Thursday, I forget which one, 3 p.m. lab. We are adding another Thursday lab. So we're changing one of the Thursday morning labs, which not many people are in. We're changing it, or we're adding a Thursday afternoon lab. We're going to combine the 2 Thursday morning ones, and it's only 4 or 5 extra people, so it's not a big deal. I will put that up later today. So if you want to add the Thursday section, if you don't like the section you're in, an afternoon one, you'll be able to do that. All right, see you guys later.